So for the last part, what I want to do is I want to now, essentially this part here, this that we just finished, kind of talked about what dipoles do in the presence of a different electric field. Some other electric field, how do dipoles respond to the electric field. Now I want to go back to the dipole itself, like this thing here, and want to ask, what does the dipole look like, particularly far away from the dipole? Very often the case is that when you're studying a dipole, you're looking at a location that ends up being much, much farther away than, or much, much greater a distance than the distance that separates the two charges. Because again, if this is, say, a molecule, then this separation here, which we'll call S, is probably like, order of magnitude like a nanometer or something like that. Where we might then be kind of looking at the electric field kind of far outside the molecule, like a meter away. So we have something that's 10 to the minus 9 compared to 10 to the 0. So, now we kind of talked already about what the general shape of the electric field lines look like. Again, you can go back to my fancy little computer drawing here. And I think I've oriented it. I flipped it, so positive is on top in this case. Oh well, whatever. So, what I want to do is I want to try to work out expressions for kind of what the electric field, what the magnitude of the electric field and the direction of the electric field is at two locations. Essentially, there are kind of two axes of symmetry that are interesting to study. So here's, again, the dipole itself, right? The positive is here, the negative is here. I'm going to put my origin kind of dead in the center, and that's what these kind of lines, are the axes. So then, if the charges are separated at a distance s, then the positive charge is located at 0, s over 2, right? That's just above the origin. And then the negative charge is located at 0, s minus 2. I don't know what I just said. 0, negative s over 2, a little bit below the origin. And then I'm going to ask myself, along the two axes, what if I'm kind of going perpendicular to the dipole? So the dipole itself has a dipole moment that is also vertical, because it points from negative to positive. We could evaluate the magnitude as well, right? It would just be, if this is plus q and negative q, then it's just going to be, whatever that q is, times the separation, s, whatever that number is. And in this case, it looks like I've oriented it so it's in the y direction. If I go perpendicular to the dipole moment along this axis of symmetry, I'm going to ask myself, what does the electric field look like kind of far from the dipole at this point here? So at some distance r, where the assumption is that r, this kind of r here, is going to be much, much, much greater than, say, s. Essentially what I'm saying up here. And then the other axis is, what if I have a point along the dipole axis, but I'm very, very far away from the dipole itself. So, and again, you can go back and look at the computer drawing. It'll tell you the direction of the electric field. But again, we should be able to reason it out. So again, I leave it as a question to you, as in, if I have this location here, then the positive charge is going to create an electric field that points away from the positive charge. And the negative charge is going to create an electric field that points towards the negative charge. And I'll let you kind of see if you can argue why these two vectors must have the same, are the same length. And so, particularly in this case, when you add the vectors together, the horizontal components cancel, and you're left entirely with a vertical component that seems to be pointing downward, or anti-parallel to the dipole moment. Where dipole moment points up, but the electric field over here seems to point in the opposite direction. Again, because the electric field lines are kind of doing this. Then, at this point here, the negative charge creates an electric field that points towards it, and then the positive charge points electric field that points away from it. But then these arrows are not the same length, such that when you add them together, there's a little bit of a net electric field that points upward. So far from the dipole, and it's the same if it's above as well, there's a dipole electric field that is, the net electric field points parallel to the dipole moment. Right? This points up, this points up. So let's actually work out the expression for what this net electric field is at this location. So what we're going to do, essentially the dipole is just two charges. So if I'm going to want to figure out the net electric field, all I have to do is find the electric field from the positive charge and the electric field from the negative charge at this location. And this location we're going to say is located at 0, negative r, where r, whatever the number is huge compared to s. And this is going to be important. So if you just conceptually imagine what's going on, right? I have a positive charge and a negative charge that are very close to one another, and I'm getting very far away from them. And like imagine if you could see like the positive and the negative charge kind of off on the horizon. As they get farther and farther away, right? Just like things on the horizon all kind of, seems like, the objects kind of like all move towards the center, as they go below the horizon. So the farther away these two charges are, even though they are not at the same location, it kind of seems like when you look off on the horizon, the two charges are pretty dang close to one another, as if they're almost on top of one another. So you might then expect that then their electric fields are essentially going to cancel each other out. And so that is essentially what we should see. So the electric field is pretty easy in this case because it's all vertical. So I will just write out the answers and let you confirm it on your own time. So the electric field from the positive charge points away, so it points down. So it's going to be negative k q over r squared. Oh, sorry. No, that's wrong. Why is it not r squared? Because the charge is not at the origin. The charge is at essentially s over 2. So the distance between the charge and this point, right? The distance r is from the origin to the point, and then there's plus this s over 2. So then, apologies, it's negative k q, and then this distance is going to be, the distance between these two locations is going to be r plus 1/2 s, or s over 2, all squared. And then the electric field from the negative charge is going to be plus, because it's going to point up. Y, all this is multiplied by y hat. So that's the electric field from the positive charge, and the electric field from the negative charge, kq, and then the negative charge is a little bit closer, because it's right below the origin, so then this is r minus s over 2, or 1/2 s squared, times y hat. So in this case, I'm going to do some factoring. So it seems like there's a k and a q I can pull out, so I'm going to pull that out. And then I'm left with this kind of weird combination of denominators where the positive one was r minus 1/2 s squared, and then minus 1 over r plus 1/2 s squared. So notice I flipped the order just because I wrote the positive number first. It's all in the y hat direction. So that is the net electric field from the dipole. That is the exact electric field. So to a computer, we could then evaluate this. But now I want to think about, again, I want to be a little bit more engaged in what I'm doing here. So I want to think about, essentially the image I gave you earlier, where I said that as you move far away from the two charges, and they're kind of off on the horizon, they're going to appear as if they're kind of essentially on top of one another. So I would expect them to essentially appear if we think about kind of how far away are these charges really, right? It must incorporate this distance r, and then it's, this minus 1/2 s and then this plus 1/2 s. But remember that we said s was very, very small compared to r. So it's like, 1 meter minus half a nanometer. It's essentially still 1 meter. This is 1 meter plus half a nanometer. It's essentially still 1 meter. So the distance between the charges and this point of interest, right, is essentially, to a good first approximation, r, right? Because essentially when you add the 1/2 s, it doesn't really change the answer. So for both the charges, right, and that's as if both the charges were essentially at the origin. So then I would expect that, kind of the first approximation, they both should have a magnitude that's something like kq over r squared. And then one of them is not r squared, but it's r and then minus a little bit. And then the other one is not r squared, but it's r plus a little bit, and then all squared. But if you think of them as being kind of kq over r squared, and then one is positive and one's negative, then you could imagine that, the charges are essentially canceling each other out. And then it's these kind of small deviations that are creating an actual net dipole moment. So what I'm going to do is, since I expect this kind of kq over r squared to be kind of first order, my kind of first order approximation, I'm essentially going to force this equation such that kq over r squared is out front. So what I'm going to do is what I'm calling force factoring. I'm going to force, if I could factor out an r squared from both of these, then I could bring out that r squared, and that would be kq over r squared. So I'm going to force factor. Now how do I factor out an r squared from this thing, or this thing? Well, essentially you just, again, kind of just force it. You make it work. So since, we can think of this as, how much room do I have? Since r, and let me do the plus, right? Plus 1/2 s. Right, that is the same thing. I can, of course, always multiply and divide by r. So that's the same thing as r plus 1/2 r over r times s. So essentially in the second term, I multiply and divide it by r. But then that gives me an r in the numerator that I can then factor out. So then that allows me to write this as r. And I factored out an r in the first term, that becomes a 1. And what's left over is s over 2r in the second term. So that's what I mean by force factoring. So then when I evaluate r plus 1/2 s squared, let me move you away. When I evaluate, because the denominator is r plus 1/2 s all squared, well, I just said that, and let me do square brackets. That was too big. Let me do square brackets for this. So, kind of inside the square, right? Essentially, the previous line said we can write that as r1 plus s over 2r. But then that's all within this kind of square, right? The square brackets. I just realized it's a play on words. Square brackets, squared. So in this case then, and then the laws of exponents means that I can then just apply the exponent to each. So then that's r squared, then 1 plus s over 2r squared. So I've factored out an r squared in that case. And then similarly, r minus 1/2 s all squared. Try to work it out for yourself and show that it's r squared 1 minus s over 2r all squared. So why is that helpful? Because now I can use this, and I'm going to write my electric dipole as we have the kind of kq, and then we've now rewritten the this as r squared 1 plus well, let's just look. Yeah, the plus comes first, of course. 1 plus s over 2r all squared, and then we subtracted the kq, and then we factored that one out to be an r squared 1 minus s over 2r all squared. And that's all being multiplied by y hat. So then I'm going to factor out the kq over r squared. And it seems then what I'm left with in this kind of big parenthesis is 1 over 1 plus s over 2r all squared, then minus 1 over 1 minus s over 2r all squared. So again, I have that kq over r squared out front, and then I have this kind of weird, I'm sorry, I forgot to zoom in, this kind of weird mathy thing going on in the brackets. Now, if I look at the thing in the brackets, again, since s, again, remember we said that since s is much, much less than r, and that's also going to be the case that then s divided by r is going to be much, much less than 1. Again, if s is a nanometer and r is a meter, then that number is going to be 10 to the minus 9. So I'm going to define this thing called epsilon as that s over 2r, which is something that is exceptionally small, because s divided by r is something very, very small. So then I divide it by 2, it's even smaller. So then it looks like I can write the electric dipole as kq over r squared, and then it's 1 over 1 plus epsilon squared minus 1 over 1 minus epsilon squared. No, the minus has to come first. I completely just screwed this up. Yeah, I switched these, didn't I? Yeah, because there was a negative here with the plus, and then there's no negative in the numerator when there's the negative in the bottom. So then it should be the minus is first with the positive, and then the plus comes second with the negative. So these should be flipped. Sorry about that. So then this should be 1 minus and then 1 plus. And similarly, it's 1 minus 1 plus. And then this becomes 1 over 1 minus epsilon all squared minus 1 over 1 plus epsilon squared, where epsilon is some exceptionally tiny value in the y direction. So then in this case, if I think about, use a different color, if I think about what this term is, 1 divided by, and then I take the number 1 and I subtract some exceptionally small thing from it, then I square it. But that thing, then the denominator is less than 1 as a result, because if epsilon was 0, the denominator would just be 1. But I'm taking 1 and I'm subtracting from it something that is small, but nonetheless I'm subtracting something from 1. So then the denominator is less than 1, which means this entire fraction is greater than 1. So I expect that this entire thing is slightly greater than 1. I mean this entire thing. Similarly, this entire thing here, that I have 1 in the denominator, and then I'm adding something absurdly small to the number 1. So the denominator is slightly bigger than 1. So then when I do 1 divided by that, the entire thing is just ever so slightly less than 1 as a result. Which means I'm taking something that's slightly greater than 1, and then I'm subtracting something that's slightly less than 1. So overall, I expect the net value to be positive, right? It's like I have 1.0001, and then I'm subtracting 0.99999. I'm going to get a very, very small number, but it's going to nonetheless be positive because that first term is ever so slightly bigger, right? And maybe let's just, again, commit those numbers down, right? If S is on order kind of an angstrom instead of a nanometer, say, and my distance is about a meter, then epsilon, in this case, is going to be on order 5 times 10 to the negative 11, which is pretty dang small. Now, here's something completely different that you have not seen before, unless you are already done with Calc 2, which I don't know if that's the case. It might be the case for some of you. That I won't go into kind of the proof of it, but I just want to point out that there's a exceptionally useful approximation. It's something called the binomial Taylor series. Again, don't worry too much about those words. Those in Calc 2 will do Taylor series at the end of the semester. Those in Calc 1 has something to look forward to. So essentially what this allows me to do is this gives me an approximation, a way to approximate this sort of binomial factor here. That's kind of 1 plus epsilon squared or 1 minus epsilon squared is a binomial. So the way I'll write it is that if you have something that looks like this, 1 plus alpha all raised to the power p. So alpha is a number and p is a number. But the requirement is that alpha is exceptionally small. Right? This must be true. Right? This must be true in order for this to work. So essentially you have, as long as it looks like kind of 1 plus something absurdly small. And alpha could be negative too, right? So that could be 1 minus something absurdly small. You just need the absolute value to be much, much less than 1. Then this is very, very well approximated by just 1 plus p times alpha. Essentially, this is the first 2 terms of the Taylor series, which you'll learn about in Calc 2. And so this then is great because it takes something that has, an exponent, and that exponent might even be like itself a fraction, which evaluating that just is gross and ugly, and replaces it with something that is very, very simple, just this kind of linear 1 plus p alpha. So this I find, this is, I always joke, my favorite approximation because it shows up so much in what we do, especially with these inverse square laws, like what we're seeing right now. So this is a good one just to kind of know. And we won't worry about kind of proving it, but using it, I do want to use right now. So let's go to those terms up here. So how could I approximate this using this formula, right? I want to simplify this if I can. And I want to simplify this if I can. So let's take them in stride. I'm going to do the plus first. So 1 over 1 plus epsilon all squared. So that's essentially the second term. There's a negative up front, but that's fine. We can put that in later. So essentially what you have to do is you have to get it to look like 1 plus alpha to the p. So first thing I might do is just bring everything upstairs. So 1 plus epsilon, and then make this negative 2. And then, indeed, I'll use a different color perhaps. This indeed becomes 1 plus alpha to the p if I make what identifications, right? So if I let p be negative 2, and I let alpha be epsilon, then I could turn my expression into 1 plus alpha to the p. So then that means that 1 plus epsilon to the minus 2 is going to be approximately 1 plus p alpha, and I said that p was negative 2 and alpha was e, so then that looks like it's 1 minus 2 epsilon as a result. And again, right above it, right? This is the 1 plus p alpha. In this case, p happened to be negative, which is why it turned into a -2. So this is a good approximation for this expression. And again, we should always kind of spot check ourselves. So what I'm saying is 1 over 1 plus epsilon all squared is approximately 1 minus 2 epsilon. And we argued above, indeed, that this thing is, right, because I have 1 and then I'm adding something absurdly small to 1. So this entire thing is something that's slightly less than 1. And that's what this is saying. It's 1 minus something that is absurdly small. So something slightly less than 1. All right, very good. Let's see. I think I need a little bit more room. So, okay, let's move it over there. And so then the other expression, we had kind of 1 over 1 minus epsilon squared. I can bring that upstairs, 1 minus epsilon to the minus 2. And again, I have to get it to look like 1 plus alpha to the p. But then I could write this as 1 plus negative epsilon, all raised to the -2. And it seems like in this case then, if p is -2, and then alpha is, in this case, -e, negative epsilon, then I can write this as 1 plus alpha all to the p. So then, what does it say? It says that 1 minus epsilon to the -2 is approximately 1 plus p alpha. The negatives cancel, so this ends to be 1 plus 2 epsilon. So again, we argued that this 1 over 1 minus epsilon squared is going to be something slightly bigger than 1, and that's what this is saying. It is 1 plus something very small. So then we can put this all together. I'm gonna erase some of this stuff. So I'm essentially gonna recopy it. So then my dipole moment, maybe I'll start just by recopying it. It was kq over r squared, and then we had 1 over, let me not make the same mistake again, 1 minus epsilon squared minus 1 over 1 plus epsilon squared times y hat. Sorry, I forgot to zoom in again. So now this is going to be approximately kq over r squared, and then 1 minus epsilon squared. I've conveniently just erased it, but we just said that that was the same thing as 1 plus 2 epsilon, and minus, and I'll highlight some things there. Then this was minus, and then we said the other term is 1 minus 2 epsilon times y hat. Let me highlight things so that we don't get lost. So this expression here, we've approximated as this, and this expression here, not including the minus sign, we approximated above as that. And then the minus sign just goes along for the ride. Yellow. So in this case, what happens? Well, notice some cancellations occur. Yeah, out of room. Force this up a line. So let's see what happens if I look to the expression on the right. Well, I have the 1, which is going to then be canceled by this 1, because there's going to be a minus 1. So this 1 and this 1 cancel one another. And it looks like this is then plus 2 epsilon. And then I have minus minus, so then another plus 2 epsilon. So then this entire thing seems to add up to 4 epsilon, where epsilon is very small. So the entire dipole electric field is being multiplied by this really tiny number. But epsilon itself was, well, here's where I can start writing things again. So E dipole, KQ over R squared. And we said this was 4 epsilon, but epsilon was S over 2R times y hat. So then what happens? Notice that the 2 cancels part of the 4. And then one of the r's, I could combine them, and so then I get the expression that I've highlighted below. Well, let me not skip a step. So it looks like it's 2ks, or 2k qs all over r cubed times y hat. And then I can identify that q times s times y hat is the dipole moment. Highlighter again. I'm running out of colors. Right, that q, s, y hat was what we called the dipole moment. So then I can write this thing on the left, right? I can write that the dipole kind of along the axis looks like it's 2k, and then it says r cubed, all multiplied by the dipole moment. It's in the same direction as the dipole moment. In this case, points up. But note, it's not a 1 over r squared, right? We've been seeing 1 over r squareds, everywhere. For a dipole, since the charges, when you're really far away, those charges kind of cancel one another, because they're kind of on top of one another. The electric field drops off not as 1 over r squared, but as 1 over r cubed. So it drops off faster. And then in class, we'll walk through and sketch the proof for the other axis. I won't do it here, right? So for this axis at this point, here's the answer, right? Ends up being kind of similar, but it's negative k over r cubed times the dipole moment. So again, it is in the opposite direction of the dipole moment, like what we argued at the beginning of this little section. So direction-wise, right, we're seeing kind of whether a point's kind of parallel or anti-parallel to the dipole. But the key here is that, or the key kind of insight we gain here is this kind of r cubed, is that dipoles drop off not as 1 over r squared, but as 1 over r cubed. Again, it's essentially that near cancellation kills the electric field and makes the electric field get weaker faster. Which again, then is why these kind of dipole forces or polarizing forces only matter if you're really close to the molecule. So if you did van der Waals forces in chemistry, those drop off very quickly, and you only incorporate those kind of at the surface of the molecule, where you're close enough that this electric field has not completely dropped away from the r cubed as a result. So again, if I were to kind of plot the magnitude of, I don't know what this is going to gain us, but the function of r, kind of a point charge kind of goes as 1 over r squared, and essentially, 1 over r cubed just means that it's dropping off even faster. So at a given location, a given distance away, the dipole electric field is going to be considerably weaker compared to if it was just a single point charge, because of that 1 over r cubed as a result. But that's kind of a key property, right? When you see these 1 over r cubes, right, essentially you're dealing with dipoles. And you even can get this with gravity too. Essentially the result of tides is there's kind of a dipole interaction going on with the water, being pulled towards the Earth and being also pulled towards the moon. So there's kind of a gravitational dipole of sorts going on there too. And you get that tidal forces go as 1 over r cubed. Same thing as what we're seeing here. All right, so we will practice kind of using this thing as well as sketching the proof of how we get this which then will incorporate this and review some of the concepts in class.